Hi everyone. Welcome back. So this is we are continuing with the fifth lecture, lecture 5, and this is the part 2. So in this part, we will actually go over the kind of duality, the dual formulation for these support vector machines, right? So in the last part of this lecture, we actually saw what Lagrange multipliers are, and given a constrained convex problem, convex optimization problem, right? We saw how we can construct the Lagrangian, right? And how we can then construct the dual by actually optimizing the Lagrangian, right? So we saw that the primal problem can be written as a min-max problem, right? So I'll just quickly recap from this. So we saw that the primal problem over here, right, is basically a inf followed by a supremum, right? And in fact, the supremum, this is exactly f of x, right? So if I optimize over my lambda, I get f of x, and minimum of f of x is my primal problem, right? And we saw that correspondingly the dual problem is a max problem, right? It's a max over an infimum, and this min is nothing but the dual g of lambda comma nu, right? So essentially we saw that the primal problem is min of fx subject to my constraints, and the dual problem is max g lambda comma nu, right? Potentially again subject to constraints, right? So the constraints basically come from, one is definitely we need lambda to be greater than equal to 0, right? Because lambda corresponds to the inequality constraints in my primal problem. But there could actually be additional constraints that come up because of my kind of optimality conditions, right? By setting the gradient equal to 0, there could be additional constraints that come up. So actually we'll see this in the case of SVM, okay? So I want you to recall this kind of formulation, okay? And now given this, we can actually construct the dual for the SVM, right? So the problem here is that this function is basically f0 of x, and essentially I can take negative of yi, right? So we saw this as well last time, and we can write this as plus 1 is less than equal to 0, right? And these terms are my fi of x less than equal to 0 for all I, right? So okay, so the first thing is Slater's condition, right? So Slater's condition, we saw last time that the Slater condition requires that my, first of all, my x should be feasible, right? So I require that there should be basically my data, right? In this case, my data should satisfy all constraints. So that basically says that the data should be linearly separable. But also additionally, we also require that there exists some x such that minus yi, or maybe there exists some xi, right? Such that minus yi multiplied by w transpose xi plus b plus 1 is strictly less than 0, right? So that means that there exists a point for which my constraint um, is strictly less than 0 for all my constraints, okay? All right, so basically, kind of given this now, we know that if the data is linearly separable, then Slater's condition will hold, okay? So now we can actually construct the Lagrangian first. Okay, so if you recall, the Lagrangian basically can be written as this form. So my fi so actually it's w over here. So sorry, excuse me. Here the optimization problem is f0 of w. So w is my optimization variable, right? And similarly over here, I have fi of w, right? So my fi of w is basically 1 minus yi of w transpose xi plus b, right? So that's exactly what comes over here. So this is my f0 of x, right? And this term is lambda multiplied by fi of x, and I'm summing over all I, okay? All right, so we have set the Lagrangian, right? And now we want to actually construct the dual, right? So if you recall, the dual formulation is g of lambda comma nu, and this term is basically the min over w of my Lagrangian, which is L of b comma lambda. Actually, it's also okay. So there's actually no nu over here. So I just have g of lambda because I have all my constraints to be inequality constraints. I don't have any equality constraints in the case of SVM formulation, right? So, all right, so I have my g of lambda equal to min of w comma b, right? Okay, so how do I do this? Well, I take the gradient with respect to w and each w, so wk, set it to 0, right? So I get this expression. I get this expression here, right? And similarly, I take the gradient with respect to b and set it to 0 and I get this expression, okay? So, all right, so that's great. So now we have from this, we have that my w is basically the sum of I lambda I yi xi, right? So the reason is because each of my wk, so from this I get, this implies actually my wk is nothing but sum of I lambda I yi of x I k, right? So I'm taking the kth coordinate corresponding to xi, and then essentially what I can do is that this basically means that my w vector is nothing but the lambda I of xi and sum over I, right? The same I can do for, and basically this term essentially implies that the sum over I lambda I yi should be 0, right? So my lambda should satisfy this. Okay, so now given this form of w and given this essentially like a constraint on my lambda, right? So this is what I was saying actually. So from your gradient, you could have additional constraints that come up in your dual problem. Okay, this is what we'll see. Actually, we'll get exactly this equality term as this constraint in my dual problem. Okay, so I have w equal to sum over I lambda I yi xi, and then what I need to do is that I need to fit in this value in my w, right? So I just need to basically kind of add the term, okay, and then you get this term. So okay, so I'll just quickly actually write down the math over here, right? So if I kind of very quickly expand this out, what do I get? This is sum over I, right? And essentially it's a sum over I terms and it's a sum over j terms, right? You will see that when you do a w transpose w, what you'll end up getting, because it's a sum over I multiplied by a sum over j terms, you'll actually get this sum, joint sum over ij, right? And I get lambda I lambda j, okay, yi yj, and these are two vectors, okay? So I have xi transpose xj. Okay, so this is what my w transpose w, and there is a half over here. So this is the first term, right? And then I have my second term, which is my sum over I lambda I, okay? And then I have my third term, which is negative lambda I yi, right? And now I have w transpose again. Okay, so my w transpose also is a sum over I, right? So I have, okay, so here maybe I can basically use this as if I'm taking a sum over j over here, right? So I'm just using the variable j basically, right? So this term will also be a sum over ij. It will turn out to be a joint sum over ij. It will be lambda I multiplied by yi, right? Multiplied by lambda j multiplied by yj, right? And then there is this xj transpose xi, right? But xj transpose xi is the same as xi transpose xj, okay? So in fact, you will see that these two terms are actually now similar, the same, right? This term and this term. So I have a half minus 1 time this, right? So in the end, I will actually be left with sum over I lambda I minus half times this joint sum over ij of lambda I, lambda j, yi, yj, xi transpose xj. Okay, so this is exactly what I see over here. So I have this half term over here corresponding to the minus half, right, plus the sum over I lambda I, right? But there is this additional constraint, right? So we require this constraint that my sum over I lambda I should be equal to 0. It's not really in terms of W, so I can't plug this in into this equation. I just need to add it as a constraint, right? So it's subject to this term being equal to 0. Okay. So what this means is that this is actually the dual problem, right? And if you recall, the primal problem was, right? What is the primal problem? The primal problem was minimum of half of W square subject to the constraint that yi multiplied by W transpose xi plus b greater than equal to 1, right? So this was my primal problem, which was also a constraint problem, right? And now I have converted my primal problem into a dual problem, right? Here my optimization parameters are W and B, okay? My dual problem has no W and B. I replace it with lambda, right? All right, so the question now is that, all right, I can construct my W, right? So I can solve this optimization problem, which is my dual problem. From strong duality, we know that both problems are equivalent, right? So we have this equivalence from strong duality, Slater's condition, basically. But the question is that given an optimal W, how can we construct a W and a B, right? So it turns out that a W can be found out easily, but to construct B, we need to actually use the notion of complementary slackness, okay? So, all right, so because we have zero duality gap, right? So I'll actually come to how we can construct W. So okay, so actually maybe we don't even need to wait, right? Because we know that W is basically follows this expression over here, right? So this is exactly the expression of W. So what this means is that given this lambda, I know that my W is exactly the sum over I of lambda I yi xi. Right, so this is exactly the sum, this is exactly W. So I sum over all my I from 1 to capital M. I take the sum over all my training data, I do yi multiplied by xi, and I multiply this lambda parameter. By the way, one more important thing over here, okay? So W in the primal problem belongs to R raised to N. N is my feature dimension, right? That's the notation that we have been using. Sometimes I've been using D. But we'll just use N right now, right? So N is my feature dimension and B is a real number, okay? But lambda, the dual problem, the dimension is actually R raised to M. So where capital M is the number of training data points. So if you recall, capital M is the number of training data points and N is the number of features. Right? So I think this piece is super critical to keep in mind. And basically what it means is that my lambda parameter, right, is actually R raised to M. So if M is very, very large, the dual problem can become problematic. And we'll actually see kind of issues with the duality because of the it also turns out it's quadratic, right? So this is one notion, one kind of issue with the dual. But conversely, it turns out that the dual problem has some good characteristics from an optimization perspective. Unfortunately, this is a little bit out of scope of this particular course. I cover it a little bit in my optimization and machine learning course. But basically, this has to do with the fact that SVM essentially is the primal problem is slightly harder compared to the dual problem from an optimization perspective. So the dual problem can be optimized much faster compared to the primal problem. The cost is that you need to construct this kernel. Okay, so basically the scalability of the SVM is somewhat limited because of this reason. Okay, so now we have seen that, okay, given this lambda, I can construct this W, right? So I'm good. I have so kind of the principal thing, the main thing is that my model is in terms of W comma B. So though I have lambda, I really can't do anything with my final model, right? Because I need to use my model to actually predict on instances, right? And if you recall, the SVM actually, right now we are using a linear classifier, right? So my model, my f of x, which is my model or my hypothesis function, and I also sometimes call it h of x. This is basically sine of w transpose x plus b, right? So it's somewhat critical for me to be able to find the w and the b in the dual problem, right? So with this I can actually construct my w. So this is good. How do I construct my my b from my lambda, right? So to do this, we will actually look at the notion of complementary slackness. Okay, so what complementary slackness says basically is that because I have zero duality gap, right? Because of strong duality, I have zero duality gap, it's Slater's condition. Given the optimal solution x star, right, and suppose lambda star and nu star are the optimal solutions of the dual. So for the case of SVM, I don't have any nu, I just have lambda, right? But given these optimal parameters, lambda comma nu in the case of the dual formulation, I know that because of strong duality, both of these must be the same, right? So then you actually do the math, you write this down, you write down the dual as infimum of x of f0x plus so on and so forth, and then you get this should be less than equal to f0 of x, right, plus this term, which is lambda I star fi xi star plus the constraints, right? These are basically equality constraints, right? So because x star is optimal, we know that this term is actually equal to 0, right? So my hi of x star is actually equal to 0, right, for my x star, because x star is feasible, right? So I think the main thing is x star is feasible in the primal. Okay, so this is the critical thing over here. So because x star is feasible, I know that this term is equal to 0, so I'm only left with this lambda I star multiplied by fi xi star. So if you recall, again, because of feasibility, fi xi star is actually less than equal to 0, right? So what this means is that this is actually less than equal to f0 x star, but then I have f0 x star over here, right? So this means that for each of my lambda I fi x star, and you know the sum of this, so sorry, yeah, so the sum of these terms, we have the following condition, right? So the condition is that we must have that the sum lambda I star fi x star is equal to 0. Why should it be equal to 0? Because I have f0 x star over here, and I have f0 x star on the right hand side as well over here, right? Plus there is this term, right? So because both of these terms are actually okay, so I have less than sign and finally I have less than sign, right? But in reality, because we need that f0 x star must be equal to f0 x star, that means that all my inequalities must actually be equalities, right? And for that to happen, I need this term to be actually equal to 0. Okay, so this means that this term is equal to 0, but we know that each of the fi x star are actually of the same sign, right? So what we know is that the lambda I star is actually greater than equal to 0, and fi x star is actually less than equal to 0. So because all of them are of the same sign, this means that if I take a multiplication of this, lambda I star fi x star is actually less than equal to 0. So it's not the case that when I take the sum of these, some of the signs cancel, right? All of these are actually negative. So what it means is that this can only happen if lambda I star fi x star is actually strictly equal to 0, right? So if you put it another way, this means that if I have those instances for which the constraint is not tight, right, then I absolutely require lambda I to be equal to 0. Okay, and if lambda star is greater than 0, then I require fi of x star to be equal to 0. Right? But I think the critical thing is that this only applies if there's no duality gap. So in some sense, the kind of takeaway from here is that we are able to, because of the duality gap condition, we are able to get that for all I, lambda I star fi x star is equal to 0. Okay. So now how does this help us? So the way this helps us is that now I can actually start with this particular formulation, right? And then I have my constraints, Okay, and then using complementary slackness, we know that whenever lambda I star is strictly greater than 0, right? So I have my lambda star, which is my vector, right? I take the ith component of this, and I take any ith component which is strictly greater than 0. Okay, now using complementary slackness, we know that if this term is strictly greater than 0, that means that the corresponding constraint, which is fi of which is the fi of the corresponding xi, right, comma w comma b, this must be exactly equal to 0. Okay, so given this, what does this mean, right? So I can take those corresponding xi's. So basically this means that the corresponding xi's are actually support vectors, right? Why is it the support vector? Because if you recall, my function fi of xi of w comma b is exactly equal to 1 minus yi multiplied by w transpose xi plus b, right? And this basically kind of comes from a few slides back, right? So I'm just going back to basically kind of recall this fact. So we have that fi of w, which is my constraint. Recall that w is my parameter. Okay, so I think one thing is maybe a little bit confusing, so sorry about that. I have used the notation interchangeably. So whenever I talk about the optimization stuff, I typically use x as my notation, right? But when I come back to SVMs, I use w as my notation, right? Because w is the parameter we are trying to optimize, and xi is my data. So whenever I'll be talking about the optimization landscape, I'll be using x as my parameter, right? X is my continuous optimization parameter. But whenever I'll be talking about the optimization landscape, I'll be talking about, I'm sorry, when I'll be talking about SVMs, I'll be talking about w and b as my parameter. Okay, so here I have fi of w, and my fi of w, if you recall, is basically this, right, which is 1 minus yi of w transpose xi plus b. So that's exactly what I use over here. Okay, so fi is 1 minus yi multiplied by w transpose xi plus b. Okay, and then if I stick this in, because I have that this is equal to 0, right, I can kind of conversely do the math, and you can see that you will get